G'day there. You're watching the Aussie BIM Guru, and today I'm going to run through a fairly thorough tutorial covering solar analysis in Revit using Rhino Inside. So I have run through this before on the channel in a little bit less detail, but I wanted to use the latest version of Ladybug tools and also incorporate some efficiencies that I've learned in the last year or two to cover a very thorough example of solar analysis. So today we'll be focusing on sun hour analysis. It's a fairly typical study, but often isn't done as well as it could be from what I've observed in the industry. It's also a common request I get from people on the channel who might be seeing older versions of this topic. So I'll be showing how you can best configure a model in order to be analysed. From there, how we can export it into Rhino, how we can process the Revit rooms for Rhino, run the solar analysis, and finally return the outcome of the results to Revit for scheduling. So it is worth noting that you can technically download the Ladybug package for Dynamo, but it generally won't work in any versions after, I believe, Revit 2019. A common query I get on the channel is, I want to do it in Revit. Well, short of using the Insight platform, which in my opinion isn't very good, there's not really many options for you just in Revit. Now, Ladybug Tools is developing add-ins for Revit at the moment, but in my opinion, if you want the best approach, typically going through Rhino is still the best and industry standard in my opinion. So if you are having trouble accessing this workflow, do keep in mind that Rhino does have a 90-day free trial and is a perpetual license as well. So if you can afford Revit, you can probably afford Rhino. Anyway, today I'll be using Revit, in this case 2020, Rhino 3D, so Rhino 7, Ladybug Tools 1.6, the latest version, and Elefront 5.0.5, the latest version, and the latest version of Rhino inside Revit at the time that I make this video. I will be using a sample model, just a basic apartment building, which I have put onto my course platform. I am planning to develop this model into something more refined in future, but wanted to place it here as a starting point and somewhere that you can access the model. So this model has been set up with the intent of running solar analysis. It's not necessarily a great design. It's really just something I've loosely thrown together and will refine in future. So it is assumed you'll have some experience using Revit and Grasshopper and Ladybug tools, hopefully. I will be showing you how to build the script from scratch, but there might be some parts that I do skip over for the more basic components of Ladybug. As well as this, I'll be using Rhino inside Revit, and I'll try to touch on most of the techniques I use along the way. And it is good if you do have a basic understanding of sun hour analysis, why we do it, what it means, and how we can use the results, because I will be sort of skimming over what we actually do with the results. Anyway, without further ado, let's jump in. If you find I'm talking too fast, feel free to slow down the playback speed of the video to 0.75 or 0.5. But yeah, let's jump in. So this is our sample model that I'll be using today. In this case, we're working with just a basic apartment model that I've thrown together. It's got a variety of model groups sort of holding it all together. But effectively we have a retail podium and then basically just a whole bunch of repeated floors of apartments. I do have a design option in this case for the shading devices in the building. So we can see by default there is no shading devices, and then after that there is. So we will look at a comparative analysis showing the impact of adding these devices to our design, as well as doing a standard sun hour analysis. So if I go to my floor plans, I'll just go to level 1, which is my typical floor. You'll notice we have a variety of 2-bedroom and 1-bedroom apartments. The main thing that you'll want to be aware of is, firstly, I have set up my apartments to cover the entirety of the actual apartment itself, rather than room by room. This is going to make it easier for us to run a study, treating this room as one testing surface. I've done this by taking the internal walls and making sure they're set to non-room bounding, which is quite a common thing to do in firms when you're working with apartment buildings in earlier design stages, where you really just need the apartment to be a single object, and you might just be showing the internal walls for context, and you won't usually split these up into rooms until later. I also have a common corridor and core in the building, not that that's really that important. And I also have a southern and a northern aspect. Now I have set up the building on a rotation as well, so we are going to have to take this into account when we're working with Rhino. So we'll need to make sure we account for this difference in north rotation, which we can see at the moment is 22.5 degrees. And we'll use that in our study as well. That's really all there is to the model at the moment. I have added a parameter that we are going to populate later, a project parameter called sun hours, which is an integer. that we have applied to rooms, and this will allow us to use a color scheme in order to understand how many hours of sun these receive. So if I select one of these apartments and I say that it gets 1 hour of sun, we can see I've got a color scheme active that is going to override this. So effectively in this view template, I have a color scheme where I've got 1, 2, 3, or 3+ hours. If I want, I can add 4, 5, 6, 7, so I can actually just expand this to 1 each maybe. So I will do that, and maybe it will just go from here to a cyan to a green. So we'll try to follow a typical ladybug color spectrum or thereabouts. So we'll go through yellows, and then eventually we'll go orange to red. And this will indicate to us roughly how many sun hours we're receiving. So at this point, we're going to want to actually take this into Rhino for analysis. We're pretty much already at that step with this model, the way it's set up. So what I'm going to do is boot up Rhino inside Revit. So typically you want to hit the start button. And then after that, we're going to enable the Rhino platform. So this is running inside the Revit model. It's worth noting that usually you're going to want your units to match Revit ideally. Currently we're in millimeters. So we have to keep that in mind whenever we're specifying a number, such as a value that you might want to put in meters, especially when we're doing things like divisions of grids, because we can end up actually crashing Rhino if we're not careful, if we put in a number that's actually 1,000 times smaller than what we're meant to be doing. So what I'm going to do here, instead of actually baking everything across using Rhino Inside, I'm just going to do some basic exports out of my model. So we're going to want to make sure that in this case we exclude the glass from our export because we're looking inside the rooms and the light can go through the glass. So I've already set up a variety of views. For example, I have a building shell where I've turned off my curtain panels so I can't see them. So this is my first export. Now I'm going to export it to FBX. I find it's really great because it's quite lightweight. And it's ideal when you're just using elements that are going to block the sun and don't need to be precisely measured. I've then got my surrounding context. So these are just some buildings surrounding the site that we can also export to FBX. Now we don't have to export the glazing because we're not actually using it for the purpose of analysis, but we will export our shading devices again to FBX. Now you can export to DWG if you want to, but I find generally there's not really a need to unless you want to work with the geometry of those objects. So for now, we're just going to deal with that instead. So I might just go back to a 3D view. Generally, when I'm working in Rhino Inside, I like to turn off preview geometry in Revit because it can make the experience quite slow in Revit if we're not careful. So I'm going to boot Rhino back up and I'm just going to begin importing these particular aspects of the model. So I'm going to bring in the building shell. It might prompt me for units and usually you're going to want to say yes. And whilst I've got these elements selected, I'm going to make a new layer. And I can just call this building shell, right click the layer and change object layer. Usually I like to change the color of layers as well, so it's really clear what layers things are on. I might just go to shaded as well. There we go. I'm now also going to import my context. And again, I'm going to create a layer while I've got this selected. Change object layer, and I'll just make this one dark gray as well. For now, I'm going to lock these layers just because I don't really want to select anything on them. I'm also going to bring in the shading devices and make a layer for them and change their objects layer as well. And I'll make those a different color because they're a little bit more important. They're a testing object that we want to remember to incorporate. But at the moment, you can see now we have no glass. We have our shading devices here in the model. And we're pretty much good to go at this point. Now I did notice a couple of elements are missing here, so I might just do a manual export of those. There should be some caps over the shading devices that I can't currently see. I think my view filter must be hiding them. So I'm just going to do a one-off export of these 4 objects as well. And just call this caps. And then I can just import these. And whilst they're on selection, I can just change object layer to shading devices. And there we go. So the next thing we need is actually our rooms, our testing objects. And we're going to want to process these as well. So we're going to use Rhino Inside to do this. I'm firstly going to save this model. And I'll just call this, in this case, my testing model. I'm going to want to probably just turn some things off so I can see what's happening. I might leave my shading devices on for context. And I'm also going to boot up Grasshopper inside Rhino, inside Revit. So I'm firstly going to have to collect all the rooms and then filter just the ones that have the word bed in their name, which are all my apartments. So I'm going to begin just by firstly saving my script. I need to place a node first, I believe. There we go. And I'll just call this working script. It's good to do that because if Rhino crashes, it also crashes Revit, but it means that we can at least get the backup of our script the next time we try to open it. So to begin with, I'm going to use Revit and I'm going to use the query categories node to get the rooms category, which you can see at the moment is located under Revit and then under object styles. So this is my favorite way to collect categories, just by name. It's very easy. It's sort of like doing it in Dynamo. So at this point, we should have the Revit room category, and I'm now going to use a filter so we can collect these objects using a category filter. I'm then going to query elements, which you can find in this case under Revit query elements. And we're going to want to remove the L input, the limit, and just get as many rooms as we can. And at this point, we should have 42 rooms, and we just want the rooms called bed. Now, there's many ways to deal with the object at this point. We can get the parameter value of name. I just prefer typically to just turn this into text, which will usually contain both the room name and number. And I can now use a text match node in order to find all the rooms that have a particular match. So I'm going to use the regex input here, which allows me to look for a particular word or phrase, which is in this case going to be bed. And we'll end up with a mask that we can apply as a cull pattern to our original Revit rooms just to get the bedrooms. So we can see now that our podium is excluded and our core is also excluded, which is exactly what we want. Now I could at this point just use these as B-reps, I believe, but I can probably also just get element geometry because you can see that was a little bit slow. So instead, I'm actually going to use the element geometry node, which is a little bit faster. And what we're going to want to do with this is find the bottom of the room. Now, there's various ways to do this. Typically, my favorite way to do this is firstly just to work with the fact that we have one solid per room. So I'm going to flatten this output. And I'm going to turn off the preview and I'm going to put a bounding box around each of these. And what I can do with this bounding box in this case is evaluate the box at a particular point. So I'm going to want to be at the bottom center of the box. I'm then going to create a plane at that point and then intersect it with the original solid of the room to get the bottom of the room effectively. So in this case, I can work at UV of 0.5 and then set W, the vertical parameter, to 0. And from this, we should have a point at the bottom of each solid, which we can now use to create, in this case, a plane. Effectively, we actually already have this plane as an output. So now we can do a B-rep plane intersects. Whoop. Wrong one. B-rep plane. So from each original shape, we're going to intersect it with that plane. Now that node's a little bit slow, it doesn't take too long, but it is probably like what you might call a bottleneck in the script. It could potentially be quite slow in jobs that have more geometry to process. But we can see there, we've got a nice, neat outline for each of these, which we can then just pass to a surface to patch these surfaces. And there we go. So now we have the bottom of each room, which effectively is suitable as a test surface. So what I'm going to do here is just break this off into a group. And at this point, we could use this as our testing object in Ladybug, but there's a problem with this. So if I go to Ladybug and I use the generate test point grid, just to visualize these objects, I'm firstly going to specify a grid size of 1000. And I'm also going to specify an offset distance as well. In this case, I could probably set the offset distance as 0. And we'll see that if we do that, Ladybug's going to attempt to generate one point at the center of each meter across this shape. But we end up with what I like to call coronas of points around areas. So you can see that when it gets to awkward points in the mesh outcome, we're going to get like pinch points like this. This really isn't ideal. and can cause quite a lot of slowdowns and problems when we run this into Ladybug. We're effectively adding bias into our results because we're going to get more points in certain areas and less points in others, which we can't really work with logically. So what I'm going to do is process these floors into equal tiles. Now I've got a tutorial on the channel a little bit like this. My methodology has since become a little bit more efficient for this, so I'm going to show you the more efficient method. So at this point, because we're dealing with what's going to become a bottleneck in our script, I like to use a stream filter. And because I've got Ladybug installed, I can use the Ladybug false start toggle. So this node effectively will switch to false every time you reopen the script. So it's great when you want to make sure that your booleans are set to false, because what happens here is whilst this is false, nothing passes through stream 0. When it's true, it does pass through stream 1. So that's ideal for us to proceed with. Now at this point, I might also just flatten this output. I want one surface per room. That's ideal. Now I could probably I might go back a step and actually flatten here, just in case we use these surfaces elsewhere in the script. That's probably better practice. So with these surfaces, I'm going to want to begin processing them, and I'm going to want to figure out if I had a grid that was X by X, distributed across this, where would the points go? And I'm going to try to do this in the most efficient way possible. So I'm going to avoid using heavy geometry classes, such as solids and surfaces, until the end. I'm mostly going to be working with numbers and points. So I'm firstly going to get a bounding box around these surfaces. Now these surfaces in this case are going to generate a flat box with no height. In principle, it's a surface. What I can do with this flat box is I can deconstruct the box because I want to find out the X and the Y domain or extents of this particular box for each apartment. So this is going to give me, in this case, domains. So the minimum and the maximum point that we're working between. I'm also going to want to get the bottom left corner of the box, and we can distribute points across our apartment floors on an equal spacing and find out which ones land within that surface to generate a more evenly generated tile surface. So I'm also going to want to evaluate these surfaces. And I'm going to evaluate my flat boxes in this case. And I'm going to work at a reparameterized aspect, so we're working between the domain. I'm going to construct point, and in this case, I'm just going to probably work at the bottom corner. So I want 0, 0, 0 as my UV, which will give me the corner. So in this case, we can see this is typically going to be different areas. We can see for this apartment, it's down here. For this apartment, it's down here. This apartment is down here. So it's the bottom left corner. So in this case, the X and the Y most negative corners of the apartment surface. And we're going to use these later to begin distributing cells across this apartment floor. So what we want to do now is actually figure out the domains and the extents and the number of tiles that we can fit across these apartments. So in this case, I'm generally probably going to use a cluster for this step, but I'll build it outside the cluster to begin with. So I'm firstly going to want to deconstruct the domains. So deconstruct domain, just to find out the extent of the X and also of the Y aspect of these apartment surfaces. I'm then going to want to find out how wide this is, so I'm going to take the end, or the start from the end, to find the distance between the ends of the X and the Y domains of these. So now I know that I have this distance to cover in the X direction and this distance to cover in the Y direction. I now need an input. In this case, I'm going to make this a number, and this is going to be my target spacing. Let's say for now my target spacing is 1 meter or 1,000 millimeters. So I'm going to divide each of these by that spacing to find out how many times this goes into this. And in this case, we're going to want to find how many we need to go beyond this. So we're going to need to round this, and we're going to use the ceiling outcome, which is going to force a round up in all cases. So from this, we now know that we need, in this case, X number of panels in the left, right, or X direction. And we need a certain number of panels in the vertical or the Y direction, normal to the Z plane. So in this case, we can work with these two outputs. We also, in this case, want to just create a single rectangle or tile domain, because we're going to create a rectangle basically, and just array this across to make our cells. So I'm going to multiply this by half in the negative direction and half in the positive direction. And the reason I'm doing this is because I want to create a rectangle domain that goes both directions from the center point in both directions. So I'm going to make a negative 0.5 multiplier. And I'm also going to make an 0.5 multiplier so that we take our overall width and we get half in both directions. From this, I can then construct the domain to create that size tile. So we'll have half in both directions in this case. At this point, I'm going to end up clustering this. So I'm going to take this input, and then I also have my X and my Y input, but I'm going to cluster like that. Now we're going to end up with some pretty awkward inputs at that point. So I am going to go and just revise this to fix a few of these up. So this is the same, so we can get rid of that. Here, this is also the same. Now we're also going to want some outputs. So in this case, if I look for output, we're going to want the ceilings of the X and the Y domain, as well as the tile domain. There we go. So now in this case, we can set our inputs for this. So we're firstly going to know that our inputs in this case is the length in the X direction, or the domain, I should say, in that direction. So I could say probably the Y domain is probably a better description. And then our other input is our tile size. We're now going to know how many X divisions we need, and also how many Y divisions we need. And we're also going to have now our tile domain. So that really neatens up that part of the script. You can use them in a lot of different places. Generally, I find that it's great to use clusters, especially when you know your script really well and you're trying to tidy it up for an end user. Now I'm going to use a value list at this point to control the options here, because otherwise people might put in an inappropriate input. So I'm just going to say in this case I've got 0.25 by 0.25 meters, and this is going to be equal to 250, 0.5 by 0.5 meters, and 1 by 1 meter, so that we know the aspect of the tile grid that we're creating. So for now, I'll just work with a meter by a meter. Now at the moment, it probably doesn't make a great deal of sense what we're going to do with this until you can sort of visually see the outcome of what we're doing here. So now that we've got this tile size, we're also going to want to, in this case, move that point at the corner by half in both directions, X and Y. And we're going to want to move that by half in that direction. So I'm going to create a vector at this point. I'm going to construct a vector. So I'll look for construct vector X, Y, Z. So I'm going to use expressions here, and I'm just going to firstly say that we want to move 0.5 by X, and we also want to move in the Y direction by half of X as well. And X is going to be that tile size. There we go. So we can begin by moving our point in the corner in the positive direction by that particular vector. So now we're actually sitting at the center of the first tile over that apartment. Now we're going to do a few things at this point, but the first thing we'll be targeting is a rectangular array, or a two-directional array, to create an array out of these points, which we're then going to place tiles or cells at to create this cleaned up version of the floor. So at this point, I want to deal with the point as my object that I'm arraying. I'm going to want to actually generate a box to array based on, which is going to have to be a cell. It's going to have to be a rectangle. So if I look up a rectangle, and I'm just going to create one centered on a point. So this is why we need that tile domain, because we're going to create a rectangular cell at each of those. So we can see now we have a little rectangle at that first point. And that is going to become our cell. And as you can guess, we're going to use the X and the Y count to distribute points across our apartments, and there we go. We can now see those points. Now we want to turn this into a mesh, but firstly we need to find all the points that do not intersect with the actual surface of the apartments, because we're currently working across, in this case, the bounding box or the flat box related to the apartment. So I'm going to take my original apartment surfaces, and turn them into a mesh using BREP mesh, which is a little bit quicker than using straight to mesh from what I've found. In this case, we can use the speed settings to just target the fastest version of turning this into a mesh. Now, at the moment, those meshes are pretty messy, but we only need them to be intersected with effectively. So that's pretty handy. Now, I might for now actually just move these up by 1 meter. We need these points to sit above in this case. So that should now move those. I'm just checking. Doesn't look like it's moved them up actually. Interesting. Of course, because it's 1 or 1,000. So there we go. It did work. So we need to be just the tiniest bit above the mesh. So I'm just going to use the number 1 in this case. So we're just above the mesh, and this means we can now mesh ray down and see which points actually hit each of those meshes. So in this case, I'm going to use a mesh ray node, and for each of these meshes, so we're going to have to graft onto those meshes, I'm going to want to check which of those points would actually hit the meshes if we move down, so -1 in the Z direction for the direction. So now, because we're grafting, we're effectively saying for each mesh, for each set of points. I'm also just going to simplify this list as well, so it's a single tree structure. And now we should have a list of points which do in fact actually hit the apartment. Now, some of them are just on the edge of the apartment, but good enough for me, it counts. So what we're going to do with these now is create rectangles at those particular points. So we're going to take this, and we're also going to take the original tile domain, X and Y. And there we go. We can see we've now created a very clean and neat representation of these floors. So I'm just going to go and turn some of these previews off. But we can see there we've created just a very efficient and quick little algorithm that effectively allows us to break down our floors into even testing objects. Now, I'll show you what's great about these. Now that I've got all these meshes, we can actually join them using the mesh join. Now, at the moment, these are rectangles. They're going to automatically get turned into, in this case, meshes if I use this particular node. And there we go. We can see we have 1 mesh per floor. There we go. And now we have 1 mesh each. Now, if I go and resample these, you're going to notice that this is going to be a very even sample. So if I use the same settings as before, they're going to be very clean. Look at that, 1 per tile. Very clean, evenly distributed, almost 0 error or bias from what I can see. Perfect. So that's a really great technique that I've used quite often, even in my own work, to really just resample surfaces into something very much workable compared to what we get with the default Ladybug mesh attempt. So I'm going to delete this in this case, and now we're dealing with these meshes, so we want to bake these into the model to use them in our next step. Some people might take these and send them through to the next step in Ladybug. I prefer to remove the need to recompute this part of the script. I find that usually this is a bit of a bottleneck in terms of speed, so I do prefer to bake these in and then use those objects. But we are going to bake in the name of the objects so that we can still reference the original Revit object using the live geometry in Rhino. So I'm just going to take this part of my script, group it up, and the next step here is going to need a couple of things. So we're going to want to use the bake component from Elephant. So I'm currently using Elephant for 5.0.5, which is in beta. There's different modes and options you can use here. For now, I'm just going to use all the defaults. So we're going to want to bake these meshes in. But I'm also going to want to bake them into a particular layer, and we're going to want to give them a name, which in this case will be the number of the apartment. So I'm going to go back a step. And in this case, in Rhino Inside, you can actually just use the element name node to get the number of the apartment, interestingly enough. And there it is. So I'm going to make that a hidden wire so I can take it over to the end of this part of the script. And we're going to want to set, in this case, object attributes, which is currently set to old in this particular one. I assume there's a different method, maybe elephant attributes. Yeah, that's way too complex for me. So for now, we're going to set this as the name of the object when we bake it. And I'm also going to define a layer as well. So somewhere in here, there's a define layer node. And if the layer doesn't exist, it will create one before it puts these objects on that layer. So I'm just going to say, in this case, this is test surfaces. Oops. For the layer name, and we'll just make the color blue in this case. So I'll use a swatch in this case for this, and I'll just make it a little bit transparent. I don't know if the transparency comes through to Rhino, but we'll try anyway. Cool. And these are the attributes that we'll send into these in this case. Now you can always add a bake name if you want as well. I might do that in case I want to rebake them. But otherwise at this point we can hit bake, and there in this case is our rooms. So I'm just going to group this up, and let's just have a quick look in Rhino at these rooms. So we can see they're a very clean mesh, and they in this case have their bake name from Elefront, and they also have their name as 5.04, 5.03, the room number in Revit, which we can go and use to recall the actual room in Revit at the end of this workflow. So at this point, we're going to switch over to using Ladybug. So if you haven't used Ladybug before, I do recommend looking at some of my older tutorials, but I'll try to cover some of the basics as we go. So let's go back over here and start creating a new branch of our script. Usually I'd make it so you effectively rerun the script at this point and start collecting these objects. So what I'm going to use is a stream filter connected to a button. And you'll see what this does in a second, but what I'm going to do is put test surfaces as both inputs. Now you might think that's a little bit stupid. Why am I using a filter with the exact same thing? But effectively this actually acts as a refresh button. So what would have happened in the script at this point is I would have made these rooms down this end of the script, but until I tell this part of the script I have actually got test surfaces on a layer, it's not going to know what to do with them. But now that we have that, we can reference by layer. And this will go and retrieve all the objects on that particular layer as referenced objects in this case. So pretty cool and pretty efficient as well. So we're just going to start creating a new branch. And now I will go back and generate test points. I do prefer to do this typically versus just sending the object straight into Ladybug. This way I have full control over the face count and the analysis mesh before I run the study versus after. And we will put that to some good use as well. So I'm firstly going to get my geometry, and I'm going to make, in this case, the grid size 1000. To be honest, it's not actually really going to matter. Typically, Ladybug is just going to put 1 point at the center of each face, especially if your testing grid is larger than your baked grid. So I'm just going to use 1000 for both the grid size and the offset distance. Now I'm offsetting by 1 in this case, or 1 meter in this case. This is quite a common requirement. It's interesting that the offset distance doesn't seem to have been applied correctly in this case. Well, it doesn't look to have been. These points aren't actually getting offset. Let's try again. Interesting. It's a bit weird that it hasn't calculated them that way. Maybe it does it later in the actual study when we apply the settings. I assume in this case it visualizes the points. Yeah, small positive number, default 0. Strange. I will use 1000 for my offset because generally when we are testing these surfaces in Ladybug, we do need to typically, in this case, test at a meter above the floor plane. But for now, I guess it looks like our analysis mesh is going to be sitting down at the floor level. So we will have to be careful with how this goes further ahead. We could always offset this mesh at this point up by a meter if we wanted to be safe, or we could use a meter later on in Ladybug and just test if it makes a difference if we make it 0. So I might just do that instead. Because I'm not always a huge fan of some of these nodes in Ladybug because it's not always clear exactly what they're doing or how they're working, which is sort of why I like to use nodes like this to visualize what's happening. So we now have our list of meshes, 1 per surface or mesh that we gave. I'm going to flatten this into 1 big mesh. And the reason I like to do this is so I can just run a sun study across a single object versus 30 objects. And I find this is always faster, at least in my testing. Now I'm also going to find out how many faces each of these meshes have. I'm not quite sure if there's a face count method in Grasshopper. I haven't come across it. So I usually just break this thing down as a string. So I turn this into a string, and I'm now targeting that number on the end. So I'm going to use a text split node. And I'm going to split this text at the F colon. Then once I have that, I can now use list item to get the second part or the last part of each of those. So I'm going to work at -1 index, the last item in the list. And now I should have that number plus a bracket. So I can use the string replace, I believe it's called, replace text. And I'm now just looking for that bracket and replacing it with nothing. And that should leave me with a string, which I can then turn into a number. And now I know how many faces each of those original meshes has, whilst running this other mesh with all those faces combined. And the way that these meshes are combined is their faces are stored in one mesh at a time in order. So I can always split these back apart after I've studied them in Ladybug. So a really handy little trick, that one that not everyone seems to be aware of, but pretty funky. So at this point I can just group this up, and this is really now my testing object ready for studying in Ladybug. So I'm going to need to do a few things. I'm firstly going to use Ladybug to construct what's called an analysis period. So I'm going to be working on a particular month. Now usually in Australia we test usually at the winter solstice. So I'm going to work on, in this case, June. And I'm also going to work between 1 and, in this case, 21 and 31 for the day. So start day and end day. I'm just doing a single day time range. So I'm just making these the same input. And then I'm going to need a start and end hour. So in this case, we usually work from 9 until 3, at least against the most common requirements that we use, which is the apartment design guidelines in Sydney. That's at least the ones I'm most used to. For the time step, this is just how many times you want to divide the result. So in this case, I'm just going to apply a time step of 4, which is going to, in this case, break us into quarter hours. And we can verify that by looking at the period or how hours of year output. Now in this case, I believe, of course, I need to make that 3 o'clock. And I can see in this case, I should have every 15 minutes, which I do. I also now need to import an EPW file, so I'm going to use Ladybug, import EPW. I usually like to go in and remove pretty much all the inputs I'm not using. In this case, the only input I need is location. And I'm going to path, in this case, to a weather file, which I've downloaded from the Ladybug weather files resource. So I will just quickly go there. If I go to Ladybug weather files, they have a really great resource where you can search for weather files around the world. So in this case, I'm saying I'm doing a study in Sydney, so I've in this case just went to the airport, looked for the IWEC resource, downloaded this and taken the EPW file. And now I can just path to that file that I've downloaded, which can then be read by Ladybug as an EPW file. From this, I'm going to create a Sunpath. So I'm looking for a Ladybug Sunpath, which I believe in this case is under Visualize Data. Yes. So we're going to need a few things at this point. I'm just going to move these down a bit. So first of all, we're going to take our HOIs, or our hours of the year, I believe that stands for. We're going to get our location. Now at this point, that's enough to actually create a Sunpath. There is a slight problem at this point. You may recall that our building was on a rotation, true north was at an angle. Now when we export FBXs, they typically will be facing project north. We could rotate the model manually, but we can also compensate for north as an input in this particular node to rotate our Sunpath rather than rotating our model. So given that I'm using Rhino Inside, I can actually go and query the site location. So using site, I think it's project location. Yes, this will give us all the points, so the survey points, project base point, etc. So from the project base point, I want to ask for the angle to true north. So if I use the element query parameters node, I should be able to find that there is actually a parameter that stores this. a built-in parameter, and we're looking for the angle to true north parameter. So I'm going to use the element parameter node and take out the value, so it's a get parameter. And I'm just going to be looking for angle to true north. And assuming the model has been set up correctly in Revit, at this point we should now have that 22.5 degrees. Now it's in radians currently, so we do have to convert that to degrees. And there we go, we can see we get the 22.5 degrees. So I'm just going to create a little group for that. And I'm going to plug in that value to the north rotation. And we can see now that our Sunpath has correctly rotated to the same position that it would be in the Revit model currently as well. So that's great. So we also have our Sunpath and our true north rotation at that point. So I'm just going to move these probably back here. Now at this point, we're pretty much ready to start setting up our sun hour analysis. So under Ladybug, analyze geometry, direct sun hours. We're going to need to give this a few inputs. Firstly, our vectors, which we can get from our Sunpath, our time step, which we've declared earlier, geometry, context, grid size, offset distance. So this is where I want to test if the offset distance seems to make a difference. If not, I'll go back and move our analysis mesh before we run the study. So we're going to need firstly our vectors. We're going to take our time step from before. Geometry and context are interesting. So what I'm going to do is set run to false. So I'm going to use a false start toggle again, so that this doesn't always run by default for run. So at the moment our study is not going to run even if it has enough inputs. I'm now going to take our geometry, which is this big mesh that we've created. Now for context, I'm just going to, in this case, take these objects probably manually. So what I might do is just unlock these layers. Now for the building and the context, I can provide these together because we always want these. So I'm just going to put these into a geometry node. And I'm also going to override their name so I can say what this actually is. But sometimes we might also want to test shading devices. So I'm just going to lock those again, and I'm just going to, in this case, select my shading devices. And I'm going to set multiple geometry, and again, rename this just so I can remember what this actually contains. Now we could reference by layer, but I do find that can be a little bit slow sometimes versus just live referencing through multiple select. So I'm now going to just turn off those particular layers, but these should now be available as analysis objects, as which we can see there. For now, I'm just going to turn off their previews. And I think I've also got a mesh preview up here as well, which I want to turn off the preview for, and also my surfaces. And somewhere in here, it looks like there must be another node that's previewing those surfaces. So I'm just going to double check. It doesn't seem like it. So it must be here. There we go. Excellent. So what we're going to do is run a single sun study. Again, the grid size, we're just going to connect this back to our test points. And for now, we'll try the offset here, but we will assess the results to make sure it looks like it actually has worked. Now for now, I'm just going to turn off my test surfaces, and I'm just going to turn off the preview for my Sunpath. And we also need to now take our context and building. So what I'm going to do is merge these for later in a second test, because we are going to want to include those shading devices in an alternative test. But for now, that's my context without the shading devices. I'm now going to run my script, and it should be fairly quick. Shouldn't take too long. There it is. And we can see it definitely has worked. So let's just verify if the meter offset seems to make a difference. I think it definitely is working at a meter because you wouldn't get all that sun on the edge of the balcony. So if I say offset distance 0, I'm pretty sure we'll get a different result. Yes, good. So we're definitely using the right offset distance. So we're working at a meter, and that makes sense because a lot of our windows have a sill height that wouldn't be receiving sunlight that close to the room if not. So we've just visualized the number of sun hours being received by each surface at this particular point. We're going to need to break this down to figure out the sun hours that each apartment receives. Now, we can use many methods to determine how to measure the sun receipt of an apartment, but the most common way we do it for high-level analysis, especially when we're working to an apartment design guideline, is just to say what is the maximum result received at a point. Now, it doesn't technically follow the detailed criteria for sunlight measurement, but it's usually sufficient for high-level analysis when you're trying to inform a design at least. We do have more detailed methods that I'm probably not really allowed to share on the channel where I work, but this is a very general sort of technique a lot of firms use. But firms should be aware that technically this isn't actually enough to determine ADG compliance, at least not if you're working by the book. So just be aware of that. So we're now going to break our results into sublists. So we have at the moment just a big list of results, and they're just taken in the order of each mesh face. Now remember, we know how many faces each mesh has, so we can actually use that to partition our result into sublists per apartment. So we can see, for example, the first list here has 348 results. If we go back to our original meshes, I can see in this case that I have a face count of 348. So we can see we've consistently partitioned our results based on the mesh face count. Very useful. I'm just going to simplify this list, and I want to find out the maximum result that occurs in this list. Usually the fastest way I find to do that is to check the bounds of the result, which will end up giving me both the top and the bottom, and I want to deconstruct that domain to find the largest value in each of them. And there we go. We should now have the maximum result recorded, which I can then round down, because we can't really count a sun hour greater than a whole. So we go down to the nearest whole sun hour, so the floor, and now we actually have each result per apartment. Before I go and bake this back into Revit itself, I'm going to run a concurrent solar analysis and show you how you can do a differential analysis to see what impact making a change on your design might have to the solar receipt. So for now, I'm just going to turn off the preview here, and I'm also just going to stop running this study. I'm going to copy it, and the only thing I'm going to change is I'm going to add more context by introducing these shading devices. So I'm now running 2 solar studies at once. I'll now rerun this, and we won't see anything for now, but we will technically have 2 solar studies that have been conducted. So this one also has its own set of results. So what we can do is actually subtract these results from each other, because they're just flat lists. So in this case, I want to find the difference between these, so how much sunlight was lost when this happened. So if I take after from before, I should end up with a positive number that reflects how many sun hours in this case were lost. Sometimes it will be 0, sometimes it won't be. I can use this in this case to recolor a spatial heat map. So using this spatial heat map, I can now represent different results on my analysis mesh. So let's say I want to use, in this case, the values of my result, and I can just take any of my result meshes as my analysis mesh. Now at this point at the moment, it's just automatically colorized everything from the domain, so 0 to about 4. And we can see the hottest spots here are where the most sunlight has been lost. So this is a really informative diagram. Now you can modify the parameters of how this looks using a legend parameters node. And this lets you tune like the minimum, the maximum, etc. So let's say that we want to say our minimum is 0 and our maximum is 3. We'll just say that as soon as we hit 3, that's what we want to see. We can also, in this case, choose different color ranges to visualize our results. If you hover over the index, you'll see all sorts of different spectrums that have been created to show particular outcomes. In this case, I'm going to use number 7 in this case. I found that looked pretty decent, even though it's not necessarily suited for this sort of study, but that makes it very obvious where the loss has occurred. It sort of flares up pretty prominently, and we can then start to assess where the most sunlight has been lost. And in this case, because we're working with shading devices at the edge of our balcony, as we expect, it's going to have the most impact sort of around these particular zones where our hoods have generally come and blocked a lot of midday sun. And we can see as well some of these side devices have actually come and blocked sunlight as well, which makes sense. So it's quite a useful result to understand the true impact that we're having on our building with our shading devices. Now during winter, you're probably not going to want to block as much sun, whereas during summer you're going to want to block more. So you can also do sun studies during the summer as well, and look at loss as a positive aspect instead. It's up to you, but if you do want to do that, you just have to come back here and modify the date and time properties as well. So we've got a differential test at this point, and we also have a set of results that we want to actually put back into Revit as values. So we've covered quite a lot of ground. We're almost there. The last thing we're going to want to do, and I'll just group these up as I go. So using this result, this floor, the sun hour per apartment, we're going to want to go and effectively retrieve that corresponding apartment and set its value. Now in this case, I have run these rooms the whole way through this script, but let's say that maybe you added more rooms and you may have a different number of rooms in here to what you used originally. A safer method here at this point is to go and find the Rhino object's name and find the corresponding room that has that number. So what I'm going to do here is just get to data nodes, and I'm just going to say in this case the wire display is hidden. So the first one we're going to want to get the Revit rooms, and this can be any number of rooms, but then we're also going to want to get the test objects. So my test objects, I'm going to go all the way back to when I first referenced these objects. And because they're referenced objects, I can ask for their Rhino properties. So using Elefront, I can actually ask these objects for their Rhino attributes. And one of these attributes is their name, which is the room number that originally generated them. So I'm going to go back and get my Revit rooms as well. And this can be more rooms than the number of rooms we're dealing with. It doesn't matter if there's more. But from these rooms, I can then ask for their name using element name. Oops, I saw it there. There it is. And I now have both the element and the name of the element in the same order. So I can use a find similar node. And I can say from my original set of numbers, where does each of those Rhino numbers occur? And I now get an index within this list of objects. So now I can use a list item to get the matching actual room object in Revit. And there we go. So I now have each room as it occurs in the Revit model at this point in time. Now I'm going to use a stream filter at the end here. I do like to use these when I'm setting element parameters. So I can just use a button to set this parameter once. It's usually my preference. So when I hit the button, it sends the rooms through. And until I hit the button, nothing goes through. And I'm finally going to be using a Rhino Inside node, the parameter node. I'm going to set, in this case, the sun hours parameter of the room by name. The value is going to be the floor, and the element will come through the stream filter. So at this point, I have the ability to basically push these values down to Revit. So let's try to make this a little bit smaller so we can see that impact in Revit hopefully immediately taking effect. So I'll just make this a little bit smaller, and maybe let's try to get a few plans. There we go, there's a few. And without further ado, let's hit the button. And there we go, we can see we've pushed those values down to the apartments. The color scheme has taken effect, so we can start to see that immediately. And there we go, we can see that we've got different results. For example, this apartment receives 6 hours, this one receives 5 at the maximum, 4, 6. But we can start to see the ones that receive 0, which is often a problematic outcome. So we've informed our design that there is a problem in that the two southmost facing apartments generally don't get any sunlight, which actually will probably put us out of compliance range if we're working to ADG. But we can see we've now created pretty much a round-trippable workflow for solar analysis from a Revit model using Rhino Inside. So we've worked within the domain of Revit for the whole workflow. So I hope it's a useful workflow and it's taught you a lot about solar analysis and Rhino Inside. So there we go. I hope you found that a useful tutorial. We did cover quite a lot of ground. So at the very least, hopefully you've learned some more things about either Rhino Inside, solar analysis, Ladybug tools, all sorts of things that we've covered during the tutorial. You can find the files for this over on my GitHub, except for the model, which you'll find on my course platform. And if you do have any future requests, feel free to reach out or leave them down below. I look forward to making future similar videos to this one and hopefully seeing you there as well. Thanks. Take care. Bye.